Attention gave RNNs a way to look back at any earlier moment, but it left one big problem untouched. An RNN still has to process a sequence one step at a time. Step 2 can't even start until step 1 finishes. On a long sequence or a huge training set, that's painfully slow because it can't be parallelized across time. In 2017, a group of researchers asked a radical question. What if you threw away the recurrence entirely and built an architecture out of nothing but attention? The result was the transformer, and it's the architecture behind every large language model you've used since, including GPT. The core mechanism is called self-attention, and it's the same relevance scoring idea from the last video, just applied differently. Instead of one RNN state looking back through a chain of memory, every single word in the sentence directly attends to every other word, all at once in parallel. Each word asks, which other words in this sentence matter for understanding me? The word it in a sentence can directly attend to the noun it refers to, 3 words earlier or 10 words earlier, with no chain in between and no fading signal. Because every token can see every other token simultaneously, this whole computation happens in one parallel pass instead of a slow step-by-step crawl. But dropping recurrence creates a new problem. An RNN naturally knew word order because it read one word after another. Self-attention looks at all words at once, so on its own it has no idea which word came first, second, or last. It's just a bag of tokens. The fix is called positional encoding. Before anything else happens, the transformer adds a small signal to each word's representation that encodes its position in the sequence. First, second, third, and so on. Now the model can tell the dog bit the man apart from the man bit the dog. Same words, different order, different meaning. A single attention pass only learns one kind of relationship at a time, but language has many kinds at once: grammar, meaning, reference, tone. So the transformer runs several attention calculations in parallel on the same input, each one called a head, and each head is free to learn a different pattern. One head might specialize in tracking which noun a pronoun refers to. Another might track which words modify which other words. All the heads run simultaneously, and their results are combined into one richer representation. This is called multi-head attention, and it's why a transformer can capture far more nuance than a single attention calculation ever could. After the attention step, each token's new representation passes through a small feed-forward network, a simple set of weights and an activation function. The same building block from our neural network video applied independently to every token. 2 more pieces keep this stable across a deep stack. A residual connection carries a copy of the original signal forward and adds it back in, so information from earlier steps never has to survive by squeezing through every single transformation. And a normalization step rescales the values after each stage, keeping numbers in a healthy range so training doesn't blow up or vanish, even dozens of layers deep. Self-attention, multi-head splitting, feed-forward, residuals, and normalization together make up one transformer block. And just like the deep networks we covered earlier in this series, a real transformer doesn't use just one block. It stacks many identical blocks on top of each other, sometimes dozens. Each block takes the previous block's output and refines it further, building progressively richer representations of the text. Early blocks might capture basic grammar, deeper blocks capture meaning, tone, and long-range context. It's the same depth equals abstraction principle from deep learning, just built from attention blocks instead of simple hidden layers. The original transformer from the 2017 paper, Attention is All You Need, was built for machine translation, and it had 2 halves. An encoder stack reads the entire input sentence at once and builds a rich representation of it, every word attending to every other word freely. A decoder stack then generates the output sentence one word at a time, attending both to the encoder's representation of the input and to the words it has already generated itself. This encoder-decoder split makes sense for translation. Read the whole French sentence, then generate the English sentence. But it's not the only way to use this architecture. GPT, which stands for Generative Pre-trained Transformer, takes a simpler path. It drops the encoder half entirely and uses only a stack of decoder blocks. There's no separate input sentence to encode. GPT just reads whatever text has come so far and predicts the next word, one at a time, using self-attention across everything that's already been generated. Because it's decoder only, GPT's attention is also restricted to look backward only, called causal or masked attention. Each word can attend to every word before it, but never to words that come after, since those haven't been generated yet. That's the entire architectural idea behind GPT, a tall stack of decoder blocks doing causal self-attention over and over. This architecture matters directly for your job. The same transformer that generates fluent text can write a convincing phishing email in seconds, which is exactly why attackers increasingly use it and why the best phishing filters now use transformers of their own to catch the subtle patterns. Security teams use transformer-based models to summarize thousands of log lines or alerts into a plain English incident summary, and to power the AI copilots showing up inside SIEM and EDR tools, answering analyst questions in natural language. Understanding that it's attention, positional encoding, and stacked blocks under the hood helps you reason about what these tools can and can't reliably do. So, to recap, a transformer replaces an RNN's slow, one-step-at-a-time processing with self-attention, letting every token look at every other token in parallel, restores order with positional encoding, captures multiple kinds of relationships with multi-head attention, and stacks many of these blocks deep, just like the deep networks earlier in this series. GPT takes this architecture and keeps only the decoder half, generating text one token at a time with causal self-attention over everything written so far. We now know what the architecture looks like, but how does it actually turn that into the text you see when you chat with it? In the next video, we'll trace how GPT works, from raw tokens all the way to the words on your screen. Subscribe so you don't miss it.